Hi guys, so today I'm going to be talking about the arburg injection molding machines at work for my presentation. I've chosen this subject because I like it. So what is injection molding? Injection molding is a manufacturing process for producing parts by injecting material into a mold. Injection molding can be performed with a host of materials, mainly including metals, glasses, elastomers, confections, and most commonly thermoplastic and thermosetting polymers. Material for this is fed into a barrel and it's essentially forced into a mold cavity where it cools and hardens to the configuration of the cavity. So this is a basic overview of your standard machine. So you've got your clamping unit, which is from there back, and it essentially applies even pressure throughout on the faces to ensure that there's no distortion in the plates or gaps or anything caused, which would let plastic leak everywhere. You've got the injection unit, which tends to be referred to as the barrel back, excluding the hopper. It tends to be referenced to as the injection unit, even though it typically means the injection cylinder. You've got a drive unit, which runs primarily on hydraulics, but you can get electrical ones. You've got the mould, which obviously is what you use to create the parts. You've got hydraulic systems, which covers the mould clamping and the drive unit occasionally, as well as the injection cylinder. You've got control systems, which is essentially a monitor on the side that allows you to look at specific settings on the machine, so apply clampage force and the depth at which the screw winds back and forth at. You've got the hopper, which is just essentially a cylindrical tube that gravity feeds material into a screw which winds it across. You've got heaters, which is displayed as these blue bands here, and they essentially allow for even distribution of heat throughout the barrel, so no plastic gets cold and essentially you end up with cold slugs that block the mould, and it's a pain in the backside to clean. And you've got cooling channels, which this display doesn't really show, but it's essentially water tubes that run throughout both sides of the plate, allowing for cooling so it doesn't overheat. The injection system, so because the screw runs through the centre of the barrel on an injection moulding machine, it displaces the inner core of raw material, thereby eliminating any source of unequal heating. The reciprocating screw is responsible for providing the majority of the thermoforming plastic. This is because the diameter of the screw increases as it approaches the tip. The plastic pellets, otherwise known as resin, are being pulled along by the flights, and the flights are compressed into tighter space and sheared or cut by the action of the turning flights. The action creates friction that mixes the pellets to a uniform consistency and heats them to the proper temperature. By the time the plastic reaches the tip, it's typically 60 to 90% of the heat required to melt it, and the rest is just supplied by the heater band. So how does the reciprocating screw hold consistent injection pressure? Well, it's done through this little system here, typically referred to as the flute jack, just because of the way it is. So the flutes are these small concave cavities here, and essentially is a passage to allow plastic through. It's typically 4, all equal size and diameter and width apart. And when enough molten plastic has filled the barrel in the front of the tip, the reciprocating screw is plunged forward to inject the resin into the mould. As the mould fills, it will try to resist the compression due to physics and pressure, which forces the check ring back against the thrust ring. This effectively locks off any back pressure to the screw and can now fully pack the mould. So it's just this here, it simply slides back and forth, and that's stationary. And when the pressure builds up, which it's set to, and you can set it on the machine, it will just simply slide across and block itself, essentially forming a one-way valve. So this is a picture of a screw. It typically averages in that size and thickness. It sort of starts to separate or change diameter from there, and it obviously ends there, as this is a separate thing. And that is to allow for the build-up of pressure, which creates the heat. So what's needed? Material, the machine, the mould, the manpower. most commonly used materials are PVC, which is corrosive plastic and produces chlorine gas, ABS, which I'm not going to try and pronounce, polypropylene, polystyrene, HDPE, which is high density polyethylene, and LDPE, which is low density polyethylene, and rubber thermoplastic, which is silicon essentially, and epoxy. So that one's a little rarer. So this is the basic overview of a simplified version of what it looks like. Material granules are fed through the hopper. Typically it's gravity fed. You can occasionally find vacuumed pressurized ones, but they're a little rare as they're mega money to buy and not much advantage to them. And essentially it just drops the pellets in to here, or the resin if you want to call it that, and the heater obviously starts to heat it, so it starts to melt. The melted material is injected into the mould cavity, so as the screw winds forwards, the plastic pellets obviously rotate, and because it changes diameter, even though this shows it as one size, it pushes it against the wall of the barrel, which is hot because of the heater bands, and it slowly melts it as well as creating its own pressure in it. By the time it gets to the tip, it is completely molten but all consistent, and obviously that will then go through the flue into the mould and create the pressure. And the mould is held under pressure as to allow even distribution of the cavities to be filled, because you don't want uneven parts for obvious reasons, or unfilled, incompleted ones, and that also helps to prevent with kickback. So once the machine is finished and the component has cooled enough to harden, it's ready to eject. So it runs on a runner stripper plate, typically followed by the core, and it will knock off the component and it should just drop down into its whatever system you've got set up to remove it. Typically it's conveyors or vacuum insulated pumps which will just pump it. Then it essentially, well, that's it, unless it's running certain pigments like purple and red, really like to produce a lot of static electricity, and it will just stick to the mould. And essentially it will, essentially we just use air knives to blow down on the tool. It's just enough to push it off. You don't need any excessive air pressure to it. Typically runs at about 80 psi, and that's more than enough to deal with it. So here's an overview of the tool animation I've created to give you a brief idea of what goes into a tool.